In a Markov decision process, an agent navigates a network of states, executing actions and receiving rapid transitions in return. The objective of any reinforcement learning algorithm is to find two specific targets: the exact optimal policy, denoted as pi star, and the corresponding optimal value function, v star. Solving this problem depends on the environment. In some cases, we possess a perfect mathematical map of all transition probabilities. In others, we navigate a black box with no prior knowledge of how the system will react. Algorithms that leverage a known transition model rely on dynamic programming. Conversely, algorithms operating without a model must learn directly from experience, relying on Monte Carlo sampling methods. Whether an agent possesses a perfect model or zero foresight, finding an optimal policy requires anchoring our algorithms in rigid mathematical boundaries. We begin with value iteration. This method successively updates a value estimate until it converges on the true optimal value function. This equation is the Bellman optimality operator, denoted as L. It acts as the engine of these updates, applied directly to a given value function v. Notice the maximum operation over the available actions. This specific term ensures the operator is strictly nonlinear. This operator functions within a specific mathematical environment, a complete Banach space under the max norm, which contains all bounded value functions. This diagram shows a 3D vector space containing two arbitrary value vectors, u and v. When we apply the operator L to both, it shrinks the global distance between them by a discount factor of gamma, which is mathematically forced to be less than 1. Because this space is complete, the Banach fixed point theorem guarantees that this contraction mapping has exactly one unique fixed point. That unique fixed point is identical to the true optimal value function, v star. By continually applying the contraction, value iteration is mathematically compelled to find it. In a computational environment, running iterations infinitely is impossible. We must eventually stop the algorithm. This inequality defines the threshold to safely halt the process. Meeting this bound triggers two mathematical guarantees. First, the derived value function is strictly within epsilon over 2 of the optimal value. Second, the extracted greedy policy performs strictly within epsilon of the optimal policy. These stopping criteria are not arbitrary guesses. They are rigid mathematical limits that bind the maximum possible error of the artificial agent. This cyclical flowchart illustrates a different approach. Unlike value iteration's single update rule, policy iteration uses a two-part alternating engine. Policy evaluation feeds into policy improvement, looping continuously. The policy evaluation step solves for the fixed point of a specific current policy. This determines the policy's exact true value. A common misconception is that these evaluated state values fluctuate. In reality, the state values returned by policy evaluation strictly increase monotonically or stay equal. They never fluctuate downward. Once evaluated, the algorithm moves to policy improvement, where a new, strictly greedy policy is derived from those evaluated states. During this step, tied action values must be broken consistently. Breaking ties randomly destroys the mathematical guarantee of convergence in finite MDPs. The cycle halts when the evaluated value equals both the policy operator and the optimality operator. At this point, the policy stops changing, proving it is definitively optimal. A finite MDP possesses a finite number of deterministic policies. Because every step yields strict monotonic improvement, the algorithm guarantees eventual convergence. Classic dynamic programming has a computational limitation. Sweeping through massive state spaces requires prohibitive amounts of computation. To handle large environments, we use asynchronous DP and real-time dynamic programming. These methods update states in place in any order, or solely along sampled trajectories. It is technically incorrect to claim asynchronous DP possesses superior strict iteration bounds compared to classic DP. Its entire advantage lies in avoiding full computational sweeps, reducing overhead without changing the theoretical bounds. This leads to generalized policy iteration, or GPI, letting evaluation and improvement interact continually without waiting for either process to fully converge. During GPI, intermediate updates will constantly cause the current policy to become non-greedy relative to the newly changing values. The system only stabilizes when a policy finally becomes perfectly greedy with respect to its own evaluated function. Achieving this efficiency requires relaxing rigid structural boundaries during the run. When the rigid mathematical transition probabilities of the environment are entirely unknown, classic dynamic programming algorithms simply cannot function. To operate in these environments, we use Monte Carlo methods. These are model-free alternatives that learn purely from sampled episodic trajectories. Monte Carlo comes with a strict operational constraint. It requires episodic tasks. State values are only updated using accumulated returns after an episode entirely terminates. When a single state is visited multiple times in one episode, the algorithm must split into one of two rules: first visit MC, tracking only the initial encounter, or every visit MC, tracking all of them. Every visit MC carries a specific mathematical drawback. Reusing trajectory segments increases short-term bias in value estimates, even though the algorithm still converges asymptotically. Because there is no mathematical model revealing the environment, we must force exploration to guarantee the algorithm eventually sees all states. Non-deterministic policies assign a small probability to all actions, providing adequate sampling. This renders forced techniques like exploring starts unnecessary. These stacked probability equations define an epsilon-greedy policy. The top formula determines the selection of the optimal action, while the bottom forces a controlled probability for all suboptimal actions, enforcing exploration without losing optimization. By the monotonic improvement theorem, an epsilon-greedy policy guarantees performance equal to or better than the target policy. However, it cannot strictly improve if the system has already reached the optimal epsilon-soft policy. Moving to a model-free environment completely replaces deterministic mathematical guarantees with fluid statistical bounds, requiring persistent exploration to find success. This matrix contrasts the two pillars of reinforcement learning directly. Dynamic programming leverages complete models and Bonnet contraction guarantees, while Monte Carlo relies on episodic sampling and epsilon bounds to map the unknown. Whether an algorithm is manipulating the maximum operator of a fixed point or correcting mismatched distributions via off-policy importance sampling, the underlying mechanics serve a single purpose. Proficiency in reinforcement learning depends on understanding exactly how strict convergence boundaries bend and adapt when the underlying data is stripped away.